Alright class, today we're going to talk about percent composition. Now, one thing I want you to kind of remember always for percent is a ratio. Percent is a ratio, is not an amount. And I need you to remember that as we keep going this semester. So, percent is a ratio. Percent is not an amount, it's a ratio. And usually when we say percent, what we mean, we usually mean mass percent. So when we say percent is a ratio, is not an amount, and usually we mean mass percent. Okay. Now, let me give you a compound, N2O3. Now, what I want to figure out, the percentage of nitrogen in this compound and the percentage of oxygen in this compound. So far so good? Okay. Now how would I figure out the percentage of nitrogen? Basically what that means is I would have to do the mass of nitrogen over the mass of the entire compound, which is N2O3 times 100, and that will give me percent nitrogen. The same thing with oxygen. If I wanted the percentage of oxygen in this compound, it would be the mass of oxygen over the mass of the entire thing, which is N2O3 times 100%. So percentage is a ratio, is an amount, and also remember percentage usually means mass percent. So far so good? Okay. So let's do this one together. So for nitrogen, the mass of nitrogen is 14. Now what I have 2 nitrogen in this compound, right? So it would be 28.0 grams of nitrogen I have. The mass of N2O3, the molar mass, if I add up 2 nitrogen and 3 oxygen, what I get is 76.0 grams times 100. What I end up getting is 36.8%. 36.8%. We're good so far? Okay. Now, can you do the same thing for oxygen? Again, if I want the percentage of oxygen in this compound, what I have to do, it would have to be the mass of oxygen, but I have 3 oxygen in this compound, right? So I have to add up all the oxygen. Oxygen has a molar mass of 16, but I have 3 oxygen, so it would be 48 grams over the mass of the entire compound times 100%, and hopefully what you got was 63.2%. You following me so far? Okay. Now technically, you didn't need to calculate the mass of oxygen. Why? If I add up these 2 together, what do I get? I get 100%. So I could just subtract 36.8 from 100% because you only have nitrogen and oxygen. So if nitrogen is 36.8%, oxygen has to be the rest. So together they have to be 100%. So percent usually means mass percent. Percent is a ratio, right? And you have to end up being 100%. So far so good? Okay, so that's percent composition. Not bad. Now what I'm going to do, I'm going to draw. Oh boy, my drawings are sometimes questionable. Okay. It looks a little bit like a pumpkin. It's not a pumpkin. It's a round bottom flask. Just go with it. Alright, here is my round bottom flask. And in this round bottom flask, I don't know what I have in this solution. Okay? So imagine you find a round bottle flask in lab, and it has some kind of solution in it, and you have no idea what this solution is. No, if you find this bottle, this flask in lab, and you have no idea what the solution is, luckily there is a technique, there is an instrument, and it's called mass spectroscopy. Okay, so we have mass spect is an instrument. You put your solution in the instrument, and what the instrument gives you, it gives you percent elemental composition. Okay, so I found this round and bottom flask in lab. It has some kind of solution in it. I don't know what it is. I'm going to put this in an instrument called mass spec. Mass spec, and then I'm going to take a mass spectroscopy of it. That's the technique. And mass spectroscopy, this technique will give me the percent elemental composition. Now, what does that mean? Here's what this means. If in this solution I have N2O3, I don't know what this is N2O3. I don't know what it is, but let's say this was N2O3. Then if I put it in mass spec, I put it in an instrument, and what the instrument is going to tell me is that this solution is 36.8% nitrogen and 63.2% oxygen, because those numbers are the percent composition of this compound. Again, I don't know what in this compound. I found this round bottom flask in lab and it has a solution in it. I'm going to take the instrument, put this in an instrument, put it in the mass spec and take a spectroscopy of it. And what I'm going to get percent elemental composition. Mass spec is going to give me percent elemental composition, and if this compound is N2O3, it would tell me 36.8% nitrogen, 63.2% oxygen. So far so good, which is great that I know what is in this compound. Okay, now hopefully you're following me so far. Now what I'm trying to get to is that if I have the molecular formula, okay, and what the molecular formula was in our last example is N2O3. When you have the molecular formula, you can easily figure out the percent elemental composition, right? Because when I told you that the compound is N2O3, you were able to easily calculate that this is 36.2% nitrogen and 63.8% oxygen, right? So if I give you the formula, you can easily figure out the percent elemental composition. Now here's the question. Can I go backward? Basically, when I put it in an instrument and the instrument gives me the percent elemental composition, it doesn't tell me this. It tells me this. It's 36.8% nitrogen, 63.2% oxygen. Can I go backward? When I have this, can I figure out the formula? The answer is yes. If the answer was no, the lecture would end right now, right? So the answer is yes, but you have to do an extra step. Okay? So the answer is yes, but you have to do an extra step. What you have to do, you have to figure out the empirical formula, and from empirical formula, then you can figure out the molecular formula. Let me make this a little bit nicer. Okay, and I'll tell you what empirical formula is. So, it's easy to go from here to here. Now the question is, can we go back? If we have the percentage, if you put it in an instrument, the instrument gives us a percentage. Can we figure out what the formula is? Yes. If you have the percentage, you can figure out the formula. You can go backwards, but it's a little bit harder because you cannot go straight. You have to go from percent elemental composition to empirical formula, and then from empirical formula, you can go to molecular formula. Now, what is empirical formula? What does empirical mean? It's basically what it means. It means the lowest or the simplest, the simplest whole number ratio. Whole number ratio is the lowest, the simplest whole number ratio. And the part I'm going to little bit circle is whole number. It has to be whole number ratio. Okay, now let's do a little side practice problem to make sure you really understand what this means, what empirical formula means. Let's say, okay, I'm gonna give you molecular formula and I'm gonna ask you to simplify them to get the empirical formula. because empirical formula is the lowest, simplest whole number ratio. Let's say I want to give you C6H6. I'm going to give you C8H14O20, and I'm going to give you H2O. If I have C6H6, can I simplify this? Can I simplify this? What do you think? Can I simplify this? Yes, you could simplify this. How can I simplify this? I could simplify it by dividing it by 6. If I do that, what do I get? I get CH. So CH is the empirical formula. This was my formula, but I could simplify it to CH. So empirical formula is the lowest, simplest whole number ratio. So the empirical formula would be CH. Alright? Now do this one on your own. C8H14O2. If I have this, can I simplify this? Yes, I can simplify it by dividing it, in this case, by 2. If I divide it by 2, I get C4H7O10. I can't really simplify more than that. So far so good. So these are the empirical formula. When they're simplified, they simplifies lowest whole number ratio. Now H2O. What would be the empirical formula for H2O? It would be H2O, right? There is no way I could simplify H2O. Okay, so again, molecular formula. This is the actual compound. This is how they exist. But the empirical formula is when we simplify this. We simplify it and we find out the lowest whole number ratio. That would be the empirical formula. You still following me? Beautiful. Okay, now let's go over this, what I'm trying to do. What I'm trying to do, we've just already done this. If I give you the molecular formula, you can get the percent elemental composition. You already did that, slide 1, right? You did this right here. This was easy. Now, can I go backward? If I give you the percentage, can you figure out the molecular formula? The answer is yes, but it's a little bit more painful because you have to go from percent composition to empirical formula, and then you go from empirical formula to molecular formula. I'm going to add one more thing to this before we move on, and that is to go from empirical formula to molecular formula. What you need molecular weight. You need molecular weight. So you need the molecular weight to go from empirical formula to molecular formula. So you need a molecular weight to go from empirical formula to molecular formula. We're good? Okay. So remember this for me. And we are going to do a practice problem now. Let's do a practice problem now. Here's our first problem. So I have a round bottom flask, still looks like a pumpkin, in lab. And my round bottom flask, I have a solution in here. I don't know what it is. I'm going to put this solution in mass spec. And mass spec is going to give me the percent elemental composition. It's going to give me 40.92% carbon, 4.58% hydrogen, rest oxygen, and it's also going to give me the molecular weight. I need to figure out the molecular formula. So I have the percentages, I need to figure out the molecular formula. Now, before I go over how you would approach this problem, the first thing we need to do is that we need to figure out the percentage of oxygen. You have the percentage of carbon, hydrogen, but you don't have the percentage of oxygen. So we need to figure out the percentage of oxygen first. But what you do know is that all of this, so this compound is made from carbon, hydrogen, and oxygen. So the entire thing has to add up to 100%. Do you agree? The entire thing has to add up to 100%. So if I take 100% and I subtract carbon and hydrogen from it, I should get the oxygen. You're so good so far. Now do that and be very careful with significant figures. That sig fig is a little bit tricky, okay? I'm going to do the sig fig over here. So I have 100%, and what I'm going to do, I'm going to subtract 40.92% of carbon from it and 4.58% of hydrogen to figure out the percentage of oxygen. You guys are following me so far? Because this compound has carbon, hydrogen, oxygen. I have these two. I know the entire thing has to add up to 100. If I subtract 100 from these two numbers, I will get the oxygen. Okay, let's do this. Now, here's the tricky part. If I actually do the subtraction, and I want you to do the subtraction. If I actually do the subtraction, which you can use your calculator to do this, it's fine. Maybe 0 and then 5 and then 4 and 5. Now, where is my sig fig? Where do I draw the line? Where things are not significant anymore? Here's the thing. 100% is the exact number. Do you agree? Yeah, 100% is the exact number. It's not something you measure, right? So 100% is not going to affect my sig fig. What I could do if I want, I can put in as many zeros as I want after 100. It doesn't matter. It's the exact number. It's not going to affect my sig fig. Okay? So what I need to figure out, basically I need to look at these two numbers to figure out my sig fig. And where do I draw the line? I draw the line after 2 and 8. This is where I draw the line. Okay, again, 100% is the exact number. It's not going to affect my sig fig. You can put a million zeros over there and do it. Put all the zeros so it's not going to affect your sig fig calculation. Now, these two are the ones that matter. I'm going to cross the line right here after 2 and 8. So everything behind this line is going to determine my significant figure. So what is the percentage of oxygen? What is the percentage of oxygen? The percentage of oxygen is going to be 54.50%. I need 4 sig fig. We're good so far? Okay. So now that we have the percentage of oxygen, we need to figure out the molecular weight. What I'm going to do, and I love rules, I'm going to give you rules. You follow the rules. You are going to be fine. Ready for rules? So every time you have this molecular formula problem, here are the rules to follow. Rule number one. What we do, we have to go from rule number one. We go from percentage to gram. Rule number one, we go from percentage to gram. Rule number two, go from gram to moles. How would you go from gram to moles? What would you use to go from gram to moles? You know that. Gram to moles, you use molecular weight. You knew that, okay? Now, number three. Then what you're going to do, you are going to divide by the smallest number of moles. Divide by the smallest number of moles. Okay? And when you do this, so percentage to gram to moles, using molecular weight, you divide by the smallest number of moles. When you do that, what you end up getting, this is not a smiley face, this is an arrow. What you end up getting a ratio. And what is this ratio? This ratio is my empirical formula. Stay with me. Once we do this problem, everything is going to make sense. Ready? Percentage to gram to moles. Divide by the smallest moles, you get a ratio, and that ratio is my empirical formula. Okay? Now here, what I have all the percentage. The first thing I need to do, percentage to gram. Now, because percentage is not an amount, is a ratio, and they all have to add up to 100%, I can take the percentage and turn them into grams. So step 1, what I'm going to say is that I have 40.92 grams of carbon. I have 4.58 grams of hydrogen, and I have 54.50 grams of oxygen. You follow that? Percentage to gram, percentage to gram. Then what I'm going to do, I'm going to convert gram to moles, right? Percentage to gram. So I took all the percentage, I turned them to gram. I can do that because they end up being 100%. And then I'm going to go gram to moles using molecular weight. You've done that many times. So 1 mole of carbon is 12.01 gram. Again, my molecular here, this is what my sig fig is. This is my sig fig because this is what I measured. Now, the correct way of doing this, even though sometimes they don't follow it, is that the molecular weight has to match that. The molecular weight has to match that because this is what I measured. This is my significant figure. Molecular weight is technically a conversion. So this has to match that. 4 sig fig, 4 sig fig to be correct. Okay, so then the grams can cancel out. What I end up getting for sig fig is 3.407 moles of carbon. Let's do the same thing for hydrogen. 1 mole of hydrogen is 1.01 gram. So the grams can cancel out. What I end up getting is 4.53 moles of hydrogen. Now let's go to oxygen. Again, I use molecular weight, 16.00 gram. I'm using molecular weight to cancel out the gram. What I end up getting is 3.406 moles of oxygen. So percentage to gram, gram to mole using molecular weight. What is the next one? You tell me. What's the next one? I can hear you. I can't hear you, but tell me anyway. You divide by the smallest number of moles. You divide by the smallest number of moles. What is the smallest number of moles that I have? The smallest number of moles I have is the oxygen. Do you agree? That is the smallest number of moles that you have. So I'm going to divide everything by 3.406. So you divide by the smallest number of moles. My smallest number of moles was oxygen, right? The smallest number of moles that I had was oxygen. Okay, if I do that, I get 1.001, I get 1.33, and I get 1.000. All right, and I'm repeating myself. Let's go over this again. So percentage to gram, gram to moles, right? Using molecular weight. Then you divide by the smallest number of moles. In this case, was the moles of the oxygen. When I did that, I got a ratio. There's one problem here. There's one problem here. We said the empirical formula has to be the lowest, the simplest whole number ratio. There was a reason I circled whole number. Do I have whole number here? This is 1, this is 1, this is 1.33. This is not whole number. And I can't really round it because 1.33, if it was 0.9, sure, you can round. But 1.33, I cannot round. And the problem is this is not a whole number. So the problem is this one right here is not a whole number, and I need them to be a whole number to get a ratio for empirical formula. So what am I going to do? Here's what I'm going to do. I'm going to multiply this by different factor until I get a whole number. You following me so far? Okay, so I want to do a little side note over here to make sure you're on the same page as me. So the problem is 1.33 is not a whole number. And if it was 0.9, I could round it, but it's not. So it's kind of far away, not a whole number. What I'm going to do, I'm going to multiply by different factor to see if I get a whole number. I'm going to multiply 1.33 times 2. Multiply by 2, I get 2.66. Whole number? Nope, not a whole number. Then I'm going to go to the next one. 1.33 times 3. Then I get 399. Okay, now I can round that to 4. Now I can round that to 4. This is not a whole number. Okay, I can 0.9, you can round it. Alright, so now what does that mean? That means I have to multiply this by 3 to get a ratio of 4. But if I multiply the hydrogen by 3, I have to do the same thing to all of them. I have to do the same thing to all of them. I can't just multiply 1 by 3 and not the rest. Okay? So, again, I multiply by 3, I get 3.99. That's very close. I can round this to 4. Okay, so now I have a whole number. That's great. But if I multiply this one by 3, I have to multiply everything by 3. All right. Now, I'm done. Almost done. I have my empirical formula. C3H4O3. What this is my empirical formula. Empirical formula, let's go back over this again. Empirical formula is the simplest, lowest whole number ratio. It's simplified. This is great. But that's not what the question asked me for. The question asked me for molecular formula. Let's go back here. I went from percent elemental composition to empirical formula. That's great. How do I go from empirical formula to molecular formula? What do I need? I need molecular weight. Okay, that's great. Mass spec gave me the molecular weight also. So mass spec said the molecular weight of this compound, whatever this compound is 176 grams per mole. So I know that the molecular weight, it is supposed to be 176 gram per mole. Okay? Now, do me a favor. Do this for me right now. Calculate the molecular weight of the empirical formula. If you do that, you will see that the molecular weight of the empirical formula is 88 gram per mole. Okay? So this is the molecular weight of that. Now, the empirical formula has a molecular weight of 88. But we know that the actual formula, the molecular formula, the actual compound, the not simplified version, is supposed to be 176. How do you go from 88 to 176? You have to multiply it by 2, right? 176 divided by 88 is 2. So you multiply it by 2. Which means, what is my molecular formula? My molecular formula is C6H8O6. That means this one right here, this is my molecular formula. Because my molecular formula was simplified by dividing it by 2 to the empirical formula of this. This is why when you get here, to go from empirical to molecular, you need the molecular weight so you can compare it. This was 88, but I know it's supposed to be 176. How do I get that? By multiplying by 2. Okay, this was a big problem, but you guys are doing really well. Ready to do a practice problem? Okay, let's do a couple practice problems. First practice problem. Okay, so read this problem. So hydrocarbons are composed of carbon and hydrogen, they're fuel. Now, you want to be hearing me talking about hydrocarbons all the time because hydrocarbons are a big deal. So hydrocarbons are compounds that are made of nothing but carbon and hydrogen. And why do we care about hydrocarbons? Because hydrocarbons are fuel. Any kind of fuel that you use are hydrocarbons. So what do you put in your car to drive it? If you have electric car, I'm not getting there. No, just your normal car. What do you put in your car before you can drive it? You put gas, right? Gasoline. Guess what gasoline is? Gasoline is a hydrocarbon. Isn't that cool? So any kind of fuel that you use, most of the time, those are hydrocarbons. They're compounds that are made of nothing but carbon and hydrogen. So next time when you need to go and get some gas for your car, what you could say is that, oh, I'm going to go and get some hydrocarbon. Yeah, don't do that. When you talk like that, people are going to think you're a little weird. But hey, sometimes it's cool to be a science nerd. So just remember this. Next time you're pumping gas, I want you to be thinking about hydrocarbon. You go, this is hydrocarbon. It's made of carbon and hydrogen. All right, so when you read this problem, you have a hydrocarbon sample that has 80% carbon, and they give you the molecular weight. They ask you to figure out the molecular formula. Now, we know how to do this. The way to do this, we go percentage to gram, gram to moles using molecular weight, and you divide it by the smallest mole to get a ratio. Yeah, let's do this. So, what I have 80% carbon. We said if you have percentage, you can just convert it to grams because they have to add up to 100%. So I'm going to say I have 80.0 grams of carbon. Okay. Now, this one is a little bit tricky. It says hydrocarbons are made of carbon and hydrogen, which means if 80% is carbon, how much of it is hydrogen? Which means 20% is hydrogen. So I have 20.0 grams of hydrogen. You're good so far? Okay. Now, percentage to gram. Now I have to use a molecular weight to go from gram to moles. 1 mole of carbon is 12.0 gram, and 1 mole of hydrogen is 1.01 gram. Okay, so the gram can cancel out and I can end up with moles. If I do that, I get 6.66 moles of carbon, 19.8 moles of hydrogen. So far so good? Okay. Now what I have to do, I have to divide by the smallest number of moles. What's the smallest number of moles? 6.66, right? So what I have to do now, I'm going to divide it by 6.66. I'm going to divide it by 6.66. If I do that, what I get 1 and I get 2.97. Now I have to think about, do I have a whole number ratio? I do have a whole number ratio. So this one is 1 and 2.97. Yes, if you have 0.9, you could round it. I could round that to 3. So yeah, this problem I went easy on you. Percentage to gram, gram to moles divided by the smallest number of moles, and you get a ratio. Okay. Now what that means is, what is my empirical formula? That means my empirical formula is C1H3. CH3 is my empirical formula. Okay, now to get to the molecular formula, I'm going to calculate the molecular weight of CH3. Carbon is 12, hydrogen is 1. I have 3 hydrogen. So the molecular weight is 15 grams per mole. Do you agree? But it tells you that the molecular weight of the actual formula, not just the simplified one, is 30 grams. So I know that this is supposed to be 30 grams. But mine right now is 15 grams. How do I go from 15 grams to 30 grams? You have to multiply it by 2. You have to multiply it by 2, which means I need to multiply my empirical formula also by 2. If I do that, I get C2H6, and that is my molecular formula. That would be my molecular formula. Sounds good? Okay. Now, before I give you the next practice problem, here's another fun fact. Barbecue, 4th of July is coming up. When you barbecue, what do you use to make the fire going? You use propane, right? What do you think propane is? And most of the almost any kind of fuel that you use in a hydrocarbon. Propane is a type of fuel. Propane is hydrocarbon. It has 3 carbon and it has 8 hydrogen. So next time you're barbecuing, I want you to be thinking about that. And it's like, oh, pass me out some hydrocarbon. I can get this barbecue going. All right, ready for last problem? Let's do one more practice problem. Here's our next practice problem. Okay, so pause this problem, do this, and then check it back with me. In this problem, I didn't give you percentage. I gave you grams and atoms. So I even made it easier for you because it was percentage to gram, gram to moles, and then divided by the smallest number of moles. So I've already given you grams and atoms. So you don't have to do the first step. All you have to do is convert the gram and atoms to moles, right? So I didn't give you percentage, but that's okay. Now all you have to do is convert the grams and the atoms to moles. So I have 195 grams of chromium, and I have 3.4 times 10 to the 24th atoms of O. What I have to do, I have to convert them to moles. 1 mole of chromium is 52.0 grams. So the grams can cancel out. What I end up getting, 3.75 moles of chromium. Okay. Now, how do I convert atoms to moles? Avogadro's number. You know that. 1 mole is 6.02 times 10 to the 23rd. So, in this problem, I didn't give you percentage. I gave you grams and atoms. So, that's even easier. You don't have to worry about the first step. You need to convert it to moles. You know how to convert grams to moles, molecular weight. You know how to convert atoms to moles. You use Avogadro's number, right? And Avogadro's number is always for 1 mole. Is always for 1 moles. Okay, 1 mole is 6.02 times 10 to the 23rd atoms. So I get 5.6 moles of oxygen. Here's the problem. The problem has not occurred yet. Now what do I need to do? I need to divide it by the smallest number of moles, which is 3.75 divided by 3.75. If I do that, what I end up getting 1 over here, and I end up getting 1.5 over here. What's the problem? The problem is that these are not a whole number ratio. 1 is, but this one, 1.5, is not a whole number ratio. What do I need to do? I need to make it a whole number ratio. Like I said before, if it's 0.9, you can round it. And otherwise, you can't really round 1.5 in this case. So what I have to do, I have to make it a whole number ratio. How do I do that? You need to multiply it by a factor to make it a whole number ratio. If I multiply 1.5 by 2, what do I get? I get 3, and that's the whole number ratio. Now, if I multiply the oxygen by 2, that means I have to do the same thing to the carbon. So I multiply carbon by 2, and I get 2. So, what is my empirical formula? My empirical formula would be C2O3. CR2. I was like, this looks a little weird. Hold on. CR2O3 is my empirical formula. Yeah? Now, I don't ask you for molecular formula here, so we are done. But if I had asked you for the molecular formula, I had to give you the molecular weight, right? So you could have compared the molecular weight of the actual formula to this molecular weight, and this to decide what you need to do to make it to be, to turn it into a molecular formula. So far so good. So percentage to gram, gram to moles, divided by the smallest moles. Make sure you get a whole number ratio, and that will give you the empirical formula. Once you have an empirical formula, if I ask you for molecular formula, then you need the molecular weight, and you need to compare the molecular weight to see where you go from there. This was a big lecture. Nice job for hanging in there. I will talk to you guys next time.